this study, we investigated the adsorption and dissociation of CO2 on copper clusters supported on copper surfaces by performing density functional theory-based calculations. The interaction of CO2 with surface is a key step in the conversion of the molecule to valuable hydrocarbons. We chose copper as model because it is cheap and is often used as catalyst for such application. Previous work showed that the dissociation process of carbon dioxide on copper surfaces is influenced by the type and by the surface structure. Interestingly, a recent experimental study demonstrated that it is possible to synthesize stable two-dimensional copper clusters supported on copper surface. With reference to these previous works, we aim to determine the influence of cluster size of such structures to the adsorption and dissociation of CO2. The figure shows the structure of adsorbed CO2, which is the initial state, the final state where the molecule dissociates into CO and O, and the transition state for the dissociation process. In this table, the activation energy needed to dissociate the molecule is also presented. The reaction energy or the indicator of the stability of the dissociated species are also listed. A lower reaction energy indicates a more stable dissociated species. Carbon dioxide is physisorbed on the surfaces. Compared to the flat copper surface, the activation energy is lower on copper clusters due to the more reactive nature of the cluster atoms. Furthermore, the dissociated species are more stable on the clusters, which enhances the ability of copper atoms to prevent dissociated CO and O from recombining into CO2. The results also show that for these systems, there is an optimum cluster size that will yield the lowest activation barrier for CO2 dissociation. Thank you very much.
Hi everyone, this is Kurt Rojas, and I'm here to present to you my research on the chemical stability of hydrogen boride sheets against water, a density functional theory study. I'd like to introduce to you my material named hydrogen boride sheet, a new boron-based nanomaterial fabricated via ion exchange from magnesium diboride. Initial studies have shown promise in catalysis and storage applications. However, many of its related material, like magnesium diboride and boron hydrides, degrade in water. The main concern of the study is the possible hydrolysis reaction in water. And here in this study, we look for signs of chemical reactions such as spontaneous degradation and strong chemical bonding. Furthermore, we apply density functional theory in our calculation to calculate structures, energies, and electronic states. To simulate the interaction, water was placed on top of various adsorption sites of the hydrogen boride sheet. Upon simulation, we have found that water was absorbed with no spontaneous structural degradation on the part of the HB sheet. Furthermore, the adsorption energies are within the physisorption energy range. We have also calculated for the highest occupied molecular orbital or HOMO, and we have found that the HOMO is preserved even after the adsorption process, signifying that there are no strong chemical bond. Finally, we have calculated for the charge density difference to observe the movement of electrons, and we have found a charge redistribution mechanism that is typical for dipole-dipole or electrostatic interaction. In summary, we have found no evidence of chemical interaction from the perspective of structure, energy, molecular orbital, and charges. Therefore, we can conclude that the HB sheet can be regarded as chemically stable against water.
Analysis of the neutron outputs and energy spectra of variable composition plutonium-beryllium neutron sources using the sources 4C code. Plutonium-beryllium 239 is an alpha neutron source with a long half-life and can be optimized by characterizing their neutron output. However, there are factors affecting this. First is that PUBE typically contains other alpha-emitting plutonium isotopes. In particular, the plutonium-241 decays into a strong alpha emitter, americium-241, which builds up and increases the neutron output. Another factor are the beryllium target atoms. The most commonly used plutonium to beryllium isotopic ratio is 1:13. However, this was found to be imprecise based on a recent chemical assay. In this study, sources 4C was used to investigate these factors by varying the beryllium target atoms and cubic compositions with weapons-grade, fuel-grade, and power-grade plutonium sources, and by decaying them up to 50 years. Varying their compositions resulted in increased neutron outputs, which are caused by the americium buildup over the years. Also, increased in beryllium content increased the neutron outputs. However, the energy spectra only showed minor deviations in the 0 to 6 MeV range as the source ages. In conclusion, both the composition and the age of the source have significant effects on the amount of neutron outputs. However, no appreciable change was observed in the neutron energy spectra.
The discoveries of molecules like water, carbon monoxide, and formaldehyde in the interstellar clouds and medium were made possible by detecting and analyzing their spectroscopic fingerprints. To get an insight on the possible reactions and underlying mechanisms and how complex molecules form, we look into the vibrational signatures of a small protonated molecular species tagged by rare gases. The protonated dinitrogen is one of the first ions in the interstellar medium. Due to its large electric dipole moment, it is considered to be a good tracer of dense gases. It is also used as a molecular probe to indirectly determine the abundance of nitrogen-containing molecules. In this work, we obtained the vibrational spectra of the protonated dinitrogen tagged by rare gases using an anharmonic ab initio approach. Characterizing proton-bound complexes such as this is vital to the understanding of proton transfer mechanism and to the impact of the astrophysical environment and various processes that lead to molecule formation. The following are the normal modes of vibration for these molecular species. The anharmonicity is incorporated into the potential energy term of the given Hamiltonian. We note that the calculated peak positions for the fundamental stretching modes of the Bayer, neon, and argon tag species are in good agreement with their available experimental spectra. One of the notable spectral features is the significant redshift of the proton stretching frequency as the rare gas tag gets heavier. A rich vibrational spectra can also be observed for the argon tag species, where the overtone and combination bands are brightened up as the energy gap between the stretching modes gets smaller. And thus we see that the rare gas tag tunes the coupling between different vibrational modes. Thank you for your attention.
Proton-bound dimers are interesting for two reasons. First, they are key intermediates in proton transfer processes. Second, they are molecular systems of interest in the astrophysical sciences. In this work, we will consider the vibrational structure for the simplest proton-bound dimer, in which the proton is surrounded by two rare gas atoms. This triatomic species has four normal modes of vibration, as shown in the screen. To simulate their vibrational structure, we use this vibrational Hamiltonian, which is expressed in scale normal mode coordinates, and we estimate intensities in terms of integrated absorption coefficients. Now, let's look at the predicted anharmonic spectra. As you can see, the asymmetric rare gas proton stretch signature, the green one here, redshifts from neon to xenon, but its intensity increases. Moreover, you see a progression of bands as shown by these red-colored bands. These are the combination bands of the asymmetric rare gas proton stretch with the symmetric rare gas proton stretch. Their intensities and the strength of these progressions increases from neon to xenon, as you could see on the picture. Now, let's examine the coupling. Using this representation, We have calculated the following matrix elements. If you examine these two adjacent states, say this one and this one, you can see that the coupling between them is very strong. Pick any two adjacent states on the main diagonal, and you get the same conclusion. This coupling overall leads to the brightening of the combination bands, which are forbidden in the harmonic picture. Thank you very much for your attention.
The study is to determine the similarities and differences of two non-equilibrium transport formalisms and compare their numerical implementation. So this is the first formalism, the Superfield Liouvillian. These formalisms are applied on RTDs. So after applying to RTDs, so this is the equation that we have. So this is the particles motion, the first term, and the second, this last term is the scattering term. So this equation considers all scattering processes or mechanisms. For the second formalism, the hierarchy equations of motion formalism, we have this equation. So the first term describes the particles motion, and the last two terms or three terms describes the scattering. But this scattering term only considers the phonon scattering. So we go to the numerical results. So these are their numerical results. So based on their numerical results, only the Superfield formalism was able to replicate or reproduce the results of the experiments. For the HAOM formalism, this did not reproduce the experiments. However, they both agree on the source of the hysteresis, which is the emitter quantization, which is the quantization in the emitter and the degrees of stability. So it affects the hysteresis of RTD. So this is the first. So this reason or source of hysteresis was first explained using the Superfield Liouvillian formalism. So to summarize, so both formalisms mostly agree with each other, but they differ on their scattering terms.
Hello, so the title of the paper I'll be presenting today is Terahertz Performance Analysis of MBE-grown indium gallium arsenide on indium phosphide films. Terahertz radiation is non-ionizing, so it is safe to use on biological tissues, making it ideal for applications related to imaging, law enforcement, security, semiconductor characterization, and telecommunications. Unfortunately, the problem we have today is that there is no material that can emit sufficiently high terahertz radiation for operational purposes, making it difficult to integrate into modern technology. Indium gallium arsenide-based photoconductors grown at low temperatures make excellent detector antennas in commercially available terahertz time domain spectroscopy experiments. So in this study, we analyzed the effects of different growth parameters on the InGaAs films, which are the growth temperature, post-growth annealing temperature, and the beryllium temperature, which affects the dopant concentration, which is beryllium. And based on the results gathered, the InGaAs film that was found to have the highest terahertz output was the one grown at 180 degrees Celsius, annealed at 600 degrees Celsius with beryllium temperature of 870 degrees Celsius, making it the most ideal for photoconductive antenna-related applications. And that is all. Thank you.